When you've completed this lesson, you should be able to do the following: simplify problems involving natural and common logarithms, and convert exponential equations to logarithmic equations. Photonic technicians need to use these functions in order to evaluate formulas, simplify expressions. They use this for common logarithms, which is base 10, and natural logarithms, which is base e. For example, the transmission of an energy through a thickness x of an absorber of coefficient alpha is defined as the expression I is equal to the incident energy, I sub 0, times e to the minus alpha x. So we'll have to work with expressions just like this as a photonics technician. So here's an example scenario. A neutral density filter has an optical density rating OD equals 0.4 between 400 nanometers and 700 nanometers. So if we have incident helium neon laser light of 632.8 nanometers, how much of that light is going to be transmitted through there? Well, we have a formula, T is equal to 10 to the minus OD power. Or if we have a thickness of a certain absorbing material is found to transmit 60.6% of the light, and we can use T is equal to e to the minus alpha t to find the absorbent coefficient of this material, that alpha value. So we'll return to these kinds of problems after reviewing some of the concepts in this module. You can use algebra skills already to isolate variables. We've learned how to take 3 plus x and solve for x. So we've found that x equals 12 by subtracting by 3 sides. Or 7x equals 21. You know how to solve for x there. You know, divide both sides by 7 and we'll get x equals 21 over 7. Or x3 equals 64. You can solve by x by taking the cube root of each side. And you find that x is equal to the cube root of 64. But how would you handle something like 3 is equal to 2 raised to the x power? How would you isolate the x there? There it's not simply a division or a subtraction or a square root or something like that that's going to help you. You're going to have to know about logarithms. And that's how we're going to proceed with this lesson today. Let's look at the powers of 10 and their logs here. Let's see if you can see the pattern. 10 is equal to 10 to the 1 power. If we take log of 10, the answer is 1. 100 is equal to 10 to the 2 power, right? So if we take the log of 100, it equals 2. 1,000 is equal to 10 to the 3 power, and the log of 1,000 is equal to 3. Are you beginning to see the pattern here? 1,000,000 is equal to 10 to the 6, and if we take the log of 1,000,000, sure enough, we get 6. Going the other direction, if we have a smaller number like 0.1 or 1/10, that's the same as 1 over 10 or 10 minus 1. The log of 0.1 is equal to negative 1, sure enough. Still enough, it still works. The exponent matches. So for 0.01, that's 10 to the minus 2, and the log of 100th is minus 2. So you can see all the way down the list how that works. So in general, we know that the log of 10 raised to the x power is equal to x. Now, by the log of 10 to the x equals x, we usually mean the log of base 10, 10 to the x equals x. We can have different bases. The common log has a base of 10. We can also have logarithms of other bases, like base of 2, right? So if 8 is equal to 2 to the 3rd power, then the log base 2 of 8 is the same as log base 2 of 2 to the 3 power, and that equals 3. So you see the log function can undo the exponent operation. We can have another example, base 2, 512 is equal to 2 to the 9th. So what do you think the log base of 512 will be? Sure enough, it's 9. Or base 16, we have this really large number is equal to 16 to the 5th power. If we have the log base 16 of that number, it'll be 5, because that's the exponent that's on the base. We can have base 4 numbers. 128 is equal to 4 raised to the 3.5 power, with the log base 4 of 128 equals 3.5. Did you notice something different here with that one? Notice that the result does not have to always be an integer. Here we had an example where it was not an integer. 4 raised to the 3.5 power, if we take the log base of 4 of that, sure enough, it comes back as 3.5. It undoes the exponent function. Just like exponents are not always integers, so we need our log function. We'll deal with that. So log base 10 of 50, well, it's not going to be an integer that gives us 50 if we raise 10 to some power, but if we raise 10 to the 1.69897 power, we'll get 50. Or we can have the log base 10 of the square root of 2, and that'll equal 0.150515 approximately, such as that if we raise 10 to the 0.150515 power, we'd get right back the value of the square root of 2. Let's look at some natural logarithms that aren't base 10. So when you see the log function with no base, you can safely assume that it's the common log with base 10. Now, there's a very special base that's known as e. Okay, and this is the value that it has, approximately 20 places. It just goes on forever and ever. It does not ever stop. It never repeats. It's a very special number called a transcendental number. And you don't need to know that, but just know that e is a very special number. So instead of log base e, we write instead ln, and it referred to it as the natural logarithm. So if e squared is equal to 7.389, we take this natural log of 7.389 and we get 2. It's the exponent on e. It's just like the log base e. Here's another example. 1,000 is equal to e to the 6.90776 and some more numbers there, and we know that because the natural log of 1,000 is equal to 6.90776 with a bunch of other numbers. Now, your scientific calculator is going to become very handy in this module because you don't know how to calculate logs or exponents without it. We used to have to look it up in tables, but now we have our handy-dandy calculators that tell us what they are. So to evaluate the log of 1,000 with your calculator, you can do this one in your head, and you can enter log on a TA80 series, 1,000, and hit enter. On a TI30 series, you have to type in the 1,000 first, and then press the log function, and the answer, of course, will be 3. So now you can verify that on your calculator. Here's another one. To evaluate the natural log of 1,000, just like before, we'll use the natural log button and then press 1,000 and then enter on the TI80 series. And on the TI30 series, you'll enter the number first, 1,000, and then the function, just like above. And again, the answer will come back 6.9077 and a bunch of other digits. Now, let's take a look at example 1. We have a helium neon laser with mirrors having reflectivities of 0.99 and amplifier length of 20 centimeters. We have to find the coefficient gain, where g is equal to 1 over 2L times the natural log of 1 over r squared. So let's substitute those values into the formula. And there's our 2L, and down here is our 1 over r, and we square it. So the first thing that we're going to have to do is square that 1 over 0.99, and we get 1.0203, and we have 1 over 2 times 20, which is 1 over 40, and we pull the 1 over centimeters over so that it doesn't get mixed up with our calculations. Now we get to use our natural log function on our calculator. So go ahead and do that, and the answer will be 0.000503 per centimeter. Or if we put it in scientific notation, it'll be 5.03 times 10 to the negative 4 per centimeter. So this laser has a gain of about 5 times 10 to the negative 4 per centimeter. Here's some calculator exercises that your text suggests that you try. So let's just take the log of 143 on the TI80 series. Remember, you have to first enter the log function, and then enter your number, and then press enter. On the TI30 series, you can do just the opposite. You put in the number first, and then tell it that you want the log of that number. And the number will be 2.1553 with some numbers after it. If you want the natural log of 65, on the TI-80 series, you put the natural log function and then 65 and then enter. Where on the TI-30, you actually go reverse and you do 65 and then the natural log function, and the answer will be 1.8129. Or if you want to divide two natural logs, this gets a little more complicated. You have to press the natural log function and then tell it that you want to take the natural log of 3 and then put in a closing parentheses in the TI-80's calculators to tell it to finish doing that, and then divide it by what comes next. So then you divide it by the natural log of 2, and then you don't have to put the closing parentheses on the ending one, and you can just press enter. On the TI-30 series of calculators, it's actually a little bit easier. Just put the 3 in and then press the natural log and it evaluates it right away, and then you divide it by 2, and then the natural log of that, and it'll perform that operation right away, and then press equals, and it'll calculate the division of those two, and the answer will be 1.5849. How about one that we should know the answer for? The log of 10,000. You know what the answer is for that, right? It should be 1, 2, 3, 4 zeros, so it should be 4. And for TI-30, you press the 1,000 and then the log, and the answer is 4. How about the natural log of e cubed? You should know what this is as well. This one you're going to have to, on a TI-80 series of calculators, you're going to have to work with those parentheses again. So you have to press the natural log button, and then you have to get to the e to the x button. So to do that, you have to press second and then e to the x, and that provides an open parentheses for the 3. And then you could press enter in this case, or you could close the parentheses for e to the x and then close the parentheses for the natural log. It's optional. But the parentheses are the very last thing on the TI-80 series. You can just press enter and it'll close it automatically. In the TI-30 series, it's much shorter. You just enter 3 second e to the x, and it'll evaluate the e cubed, and then you turn around and press the natural log function, and it'll perform that, and the result will be 3. Now, let's see how we use log to help us with algebra. Just like we used algebra to solve addition, subtraction, and multiplication and division problems, now we're going to learn how to use logarithms with exponents. As you know, log 10 to the x equals x, so if we have some function of f that's equal to 10 to the x and we take the log of it, we can take the log of both sides and we'll end up with the log of 10x, which we've now learned is x. So the log of that function will equal x. So here's a way to get to the x in that expression up above. Similarly, for a function that's a natural log, if we have e to the x, then we take the natural log of both sides, and the natural log of e to the x will equal x. And on the other side, we'll have the natural log of whatever's on the other side. So if we have any kind of expression over here that's equal to e to the x, then we can take the natural log of both sides, and this will be our other expression there, and that'll equal x. So in general, for any function f that's equal to b to the x for any base, then we can put the log base b of that function f, and that'll equal x. So that's a powerful thing to remember there. So you might want to take note of that and circle that in your textbook. So let's take a look at example 3 in your text. Say that we're given y is equal to 10 to the 2x, and we have to solve for x. The solution to that is, first, let's reverse our given equation so that we'll have x on the left side. Then we'll take the log base 10 of both sides, just like we saw in the previous slide. Take the log of this function, and it equals log of y. And the exponent will come down from the base and give us 2x is equal to log of y. Well, one more step. We have to divide both sides by 2, and x will equal log of y divided by 2. So how about a second example here? We're given y is equal to e to the negative 3x power, and we have to solve for x. Again, let's reverse the equation so that x is on the left side where we'd like it to end up, and take the log base e, or the natural log of both sides, This, of course, will undo the exponents here, and it'll come down to minus 3x. And on the right side, we just have the natural log of the variable y. And we divide both sides by negative 3, and x will equal negative of the natural log of y over 3. Let's now look at the solution to the opening scenario. We're now ready to tackle that problem. So a neutral density filter has an optical density rating of 0.4 between this wavelength range. Which percent of our helium neon light, which is in that range, does that filter transmit? We can use our expression T is equal to 10 to the minus OD power, where we substitute the value for OD into the formula, 10 to the negative 0.4, that's our OD value, and we can evaluate that as 0.398 rounded. If we do that on a TI 80 series of calculators, it's 10 raised to the negative 0.4 and then press enter. And on a TI 30 series, we have to put 10 and then y to the x power and then tell it what we want x to be, and we want it to be 0.4 and then change the sign to negative and then equals. So it's a little cumbersome working with the y to the x function. So the filter transmits 0.398 or about 39.8% of the incident laser beam. Now, the second part of our opening scenario problem, where the thickness T equals 5 centimeters of certain absorbing material, is found to transmit 60.6%. And we're going to use T is equal to e to the minus alpha, little t, the thickness, to find the absorption coefficient alpha of this material. So we're looking for alpha in this case. So to solve for that formula for alpha, then substitute the values for T and calculate the values for alpha. So we'll reverse the order like before to get the alpha on the side that we'd like it to be on. Take the natural log of both sides, and the natural log because we're dealing with the base of e this time, and simplify. So we know that the natural log function is going to bring down the exponent to minus alpha t equals the natural log t on the right-hand side. Now we need to go ahead and divide both sides by negative t. Now we can substitute in our value of 60.6% or 0.606 for the capital T and our thickness of 5 centimeters and evaluate that expression, and we'll get alpha is equal to 0.10 per centimeter. So we'll do some practice exercises here. As before, we won't do all of the exercises, but just enough to give you the confidence to complete the rest on your own. Exercise 1 asks us to evaluate several of these logs. And can you make a generalization about the log 10 to the nth power? Well, using a TI 80 series of calculator, you've already seen how to enter the log of 10. Raised to the 0 power would be enter that, and the answer is 0. Log of 10 raised to the 1 power, we'd get back 1. It looks like the calculator's working right, doesn't it? So log of 10 raised to the 2 power, and we get 2. And so forth. I don't think we need to do any more. You understand what's going on. And so that you can see that the log function undoes the 10 to the x function. So in general, log with base 10 to the nth power equals n. Exercise 3 presents us with the optical density problem, and we looked at the OD earlier. The optical density of all these light filters and goggles that you wear in the laser lab and so forth are defined in terms of their transmittance. So OD is equal to negative log of T. So we can find the OD instead of being given the OD. So we can find the optical density of a certain glass that transmits 1% of the light. So we substitute in the value of the T and evaluate it. What is the negative log of 0.01? On a TI 80 series of calculator, you have to press the change sign negative log 0.01 and press enter, and you'll get your result. And on a TI 30 series, you enter the value first, 0.01, and then press log, and then change the sign to make it positive. And then OD will equal 2. So this glass has an optical density of 2, which you probably knew already, because it's a log of 100th, 10 to the minus 2. Exercise 4 asks us to find the absorption coefficient alpha of a laser propagating at a transmittance of T is equal to 0.53 through 4.5 centimeters of absorbing medium. Using this formula, alpha is equal to negative natural log of t divided by x. So we'll substitute in the values of t and x and evaluate that expression for alpha. Alpha is equal to the natural log of t, 0.53, and x is 4.5, and the result is alpha is equal to 0.14. And you can see how that happens easily on a TI-80 calculator, just like on the previous problems, except this time we have to divide by 4.5. And similarly on a TI-30 series, you enter the number, the contents of the natural log first, and then operate it with the natural log function and divide it by 4.5, and then you have to change the sign and then press equals. So this medium has an absorption coefficient of alpha equals 0.14 per centimeters. Exercise 5 says that if you're given y equals e to the 10x, then solve for x. To get at the exponent, you know what to do. We take the natural logarithm of both sides, since the base of our exponent is e. So we'll take natural log of e and natural log of e to the 10x and simplify. And we know that the 10 to the x will come out of the exponent now and be by itself. And we'll divide both sides by 10. So the natural log of y over 10 equals x. So x equals natural log of y over 10. And that concludes our treatment of exponents and logarithms for mathematics for photonics technicians. I hope that you'll have the confidence now to go back and finish all of those practice exercises on your own, and you'll be ready to work with algebraic expressions that include both powers and roots and exponents and logarithms. All right, have a great day and see you next time.